Okay, good morning, everyone. In the last class, we have discussed about group 17 elements, right? Group 17 elements and the main compounds or the main elements that comes under group 17, that is halogens, right? Then we have discussed about chlorine, its preparation, properties and uses, isn't it? So now we are moving to the next compound, that is hydrogen chloride. Okay, X1 hydrogen chloride. So it's a compound formed using this halogen, chlorine. It will react with hydrogen to form this hydrogen chloride or HCl. What's the nature of this HCl? Actually, is it a gas or liquid? You can tell me, children. HCl.
Liquid.
Is it a liquid?
Yes.
Yes. Yeah, actually it's a gas and it's liquid form, or we can liquefy this gas into the form of liquid, that is it can be available in the form of gas and liquid. Okay, in labs we will use this hydrochloric acid as liquid. Actually it's in the form of a gas. Okay, so now we are moving to hydrogen chloride or HCl. HCl. Okay, so in the case of this HCl, actually Glauber, that's the name of the scientist, he prepared this acid in 1648. Glauber. Okay, he prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Okay, common salt, that is NaCl, with concentrated sulfuric acid. That's the method of preparation for the first time by Glauber. And Davy in 1810 showed that it's a compound of hydrogen and chlorine. Later, it is confirmed that it's a compound made up of hydrogen and chlorine. So the first preparation in laboratory, that's the same method adopted by Glauber. Okay, so Glauber, he prepared this hydrogen chloride or HCl for the first time, and he prepared it from common salt and sulfuric acid. Okay, later Davy, that's the name of the scientist, who confirmed that there will be hydrogen and chlorine in this hydrogen chloride. Okay, then first one, preparation in lab or the laboratory method of preparation of this hydrogen chloride. First method, sodium chloride, that is NaCl plus H2SO4, sulfuric acid. It will give sodium hydrogen sulfate and HCl. Okay, by heating the sodium chloride with sulfuric acid, this hydrogen chloride will be obtained along with sodium hydrogen sulfate. Clear, children? And the temperature should be maintained 420 Kelvin. Okay, 420 Kelvin. That's the first method of preparation of hydrogen chloride from sodium chloride and sulfuric acid. All of you, please switch on your videos. Switch on your videos, children. Okay, then the second one, from this sodium hydrogen sulfate. Okay, we know that there are two products obtained in the first step, hydrogen chloride, then sodium hydrogen sulfate. This sodium hydrogen sulfate again react with sodium chloride at 823 Kelvin. Okay, at 823 Kelvin, the temperature higher than the previous reaction. The first step, it is 420 Kelvin, then again higher temperature 823 Kelvin. The sodium sulfate and HCl is formed. Okay, so this is the method of preparation of hydrogen chloride. The first step, sodium chloride and sulfuric acid, then hydrogen chloride and sodium hydrogen sulfate is formed. This sodium hydrogen sulfate again react with sodium chloride at higher temperature, then sodium sulfate and hydrogen chloride is formed. Clear? And this HCl gas, it can be dried by passing through concentrated sulfuric acid. We have learned the property of sulfuric acid, right? It's a good dehydrating agent. Dehydrating agent means it will remove the water from other molecules. So we can pass this hydrogen chloride gas through sulfuric acid, then it will be more dry. the water content will be absorbed by sulfuric acid. Clear, children? That's the laboratory method of preparation of hydrogen chloride. Then we are moving to the properties of this hydrogen chloride. It's a colorless gas with pungent smell. Here also, its smell is very difficult for us to breathe. Okay, it's a pungent smell, but not a rotten smell like the previous one, ammonia. Okay, but here that's a pungent smell that's very difficult for breathing. In the case of ammonia, it's a very rotten smell. Clear? And it's a colorless gas. Then the second property, it is extremely soluble in water. It is extremely soluble in water. So here you can see the reaction HCl plus H2O. Hydrogen chloride, it will react with water to form H3O plus. We know that in the case of all acids, they will donate H plus ions, right? And this H plus ions, it will combine with water molecule to form H3O plus. Because this existence of H plus ion in a free state, that's not possible. That's why they will combine with water molecule to form H3O plus. Clear? HCl, it will be dissociate into H plus plus Cl minus. But this H plus ion cannot exist alone in free state. So it combined together with water molecule to form H3O plus, that is hydronium ion. Clear? So that's the product formed here, H3O plus plus Cl minus. So its aqueous solution is called hydrochloric acid. That's available in the form of liquid. Actually, it's a gas. It's highly soluble in water. And when they react with water, hydronium ion and chloride is obtained. Okay, so its aqueous solution is called hydrochloric acid. Clear, children? When this hydrogen chloride gas, it is passed through water, this hydrochloric acid will be obtained. That's available in liquid state. Is this clear about the third point? And one more thing, it has a high value of dissociation constant. In this hydrogen chloride, it has a high value of dissociation constant. That means it's a strong acid. High value of dissociation constant means it is very much ready, or it always ready to dissociate into the form of ions, H plus and Cl minus. So the molecules or atoms that get donate H plus ions, they are considered as acids, right? So they have a high value of dissociation constant Ka. It indicates that it's a strong acid. Clear? Yes. So along with the second point, you can add this one. High dissociation constant. That's in the textbook. Just mark that. Okay. High dissociation constant. That means it's a strong acid. Strong acid. High value indicates that it's ready to dissociate into the form of ions. The ions here, H plus and Cl minus. The molecules or atoms that will donate H plus ions are considered as acids. So here it's a strong acid in water. Okay. Then we are moving to the fourth one. This hydrogen chloride or hydrochloric acid, it will react with ammonia. Okay. NH3 plus HCl, it will give NH4Cl, that is ammonium chloride. So this ammonia, it will react with hydrogen chloride or hydrochloric acid to form ammonium chloride. Okay. So here, the formation of this ammonium chloride can be confirmed by white fumes. White fumes will be evolved. When this hydrogen chloride or hydrochloric acid mixed with ammonia, then white fumes will be formed that indicates the presence of ammonium chloride. Evelyn, yeah.
We should mark the boiling point and melting point also.
Yeah, should not clear once again.
Boiling point and melting point.
Yeah, you can also mark that. Yes. It's easily liquefied to a colorless liquid. Boiling point, it is 189 Kelvin. and freezes to a white crystalline solid freezing point, that is 159 Kelvin. It can be easily liquefied to liquefied. That's why we can convert the gaseous form of hydrogen chloride to hydrochloric acid, right? And its boiling point, that is 189 Kelvin. And if it will freezes to a white crystalline solid, their freezing point is 159 Kelvin. Clear? Evelyn, can you please read the points?
Yes, ma'am.
Okay.
Preparation in lab. NaCl plus H2SO4 gives NaHSO4 plus HCl. NaHSO4 plus NaCl gives Na2SO4 plus HCl. Properties. It is colorless gas with pungent smell. It is extremely soluble in water. HCl plus H2O gives H3O plus plus Cl minus. Its aqueous solution, it is called hydrochloric acid. It reacts with ammonia. NH3 plus HCl gives NH4Cl. And it is
So, shall I move to next one, children? Okay. So it reacts with ammonia to give ammonium chloride. That's dense white fumes. I told you. Then the next property. When 3 parts of concentrated HCl are mixed with 1 part of concentrated HNO3, we get aqua regia. Okay, that's the ratio between HCl and HNO3. HCl, that is 3. 3 part means the ratio is 3:1. Okay, that is HCl is to HNO3. When we are preparing a mixture with HCl and HNO3 in a ratio 3:1, aqua regia will be formed. Okay, aqua regia. And the main purpose or use of this aqua regia, it is used for dissolving noble metals. Which are the noble metals? Noble metals. Anyone?
Gold.
Yeah, gold, silver, platinum, etc. These are the noble metals. So this aqua regia, that mixture, it will help us to dissolving this noble metals in that liquid. I think you all are familiar with this one in 10th standard. There will be a question related to that. Some woman came and soaked the gold bangles in this mixture, and after she gave back that to the person, and the color or weight reduces. What's the solution? That identify the solution. So that's aqua regia. Okay, when we are dipping this noble metals in aqua regia, it will dissolve that noble metals. Okay, so the amount of this noble metals, it will reduces. Clear? So here, when 3 parts of concentrated HCl are mixed with 1 part of concentrated HNO3, we get aqua regia. This is used in dissolving noble metals. And here you can see the reaction AU. AU, that's gold. It will react with, here this is the mixture and it is represented in the form of ions. Okay, you know that HNO3 and HCl is there. So H plus ions, then NO3 minus, then just wait. Yeah, here it is 3, NO3 minus, and 4Cl minus. It will react together to form gold chloride. Okay, AuCl4. That means the gold portion that is dissolved in this solution. And nitrogen oxide, water molecule will be formed. So this aqua regia, it will used for dissolving noble metals. And you can see the next example that's also based on this. Platinum, it's also react with this aqua regia. Aqua regia contains HCl and HNO3. So we can write this as ions, H plus ion, then NO3 minus, and chlorine, Cl minus. Here also this platinum dissolved in that solution. That's why platinum chloride will be formed. Okay, so this is the property of aqua regia. It's a mixture of HCl and HNO3 in the ratio 3:1. Then the fourth one, this hydrochloric acid, it will decompose as salts of weaker acid. Okay, when this hydrochloric acid, it will react with salt of weaker acid, it will be decomposed. Here you can see Na2CO3, then NaHCO3, Na2SO3. These are the different salt. It will be decomposed. Okay, decompose to sodium chloride, then H2O and carbon dioxide. Here respective salt, water molecule and carbon dioxide is formed. Same product will be obtained. Okay. So hydrochloric acid, it will decompose salts of weaker acids. Okay, you can see Na2CO3, NaHCO3, Na2SO3. These all are weaker acids. Okay. Salts of weaker acids. It will combine with hydrochloric acid to form salt, water, carbon dioxide. Clear, children? Actually, the salt is formed from base and acid, right? So here one weaker acid and base combine together to form the salt. That's why it is known as salts of weaker acid. Clear? And can you guess which acid is present in the salt? Na2CO3, then NaHCO3, Na2SO3. So can you tell me which acid is present? From which acid the salt is prepared? We know that salt and base combine together to form salt and water, right? Sorry, acid and base combine together to form salt and water. So here it's a weaker acid plus base give the salt. So which weaker acid will be present there in the salt? This Na2CO3, NaHCO3, Na2SO3, etc. The first two cases it is H2CO3, carbonic acid, and in the second one it is H2SO3, sulfurous acid. These two are the weaker acids present in the salt. And along with that, sodium hydroxide will be there. Clear, children? So that's about the reaction of hydrochloric acid. So these are the properties of hydrochloric acid. Okay. Colorless gas with pungent smell, then they are extremely soluble in water, and hydrochloric acid will be formed when this gas is dissolved in water. Then it reacts with ammonia and white fumes, that is ammonium chloride will be produced. And next one about aqua regia, that's a mixture of concentrated HCl and concentrated HNO3 in the ratio 3:1. They will dissolve noble gases. Then the next property, hydrochloric acid decomposes salts of weaker acids. Is this clear? Yes. So next we are moving to the uses of this hydrogen chloride or hydrochloric acid. So Sharon, can you please read the uses?
It is used in the manufacture of chlorine, NH4Cl and glucose from cornstarch, for extracting glue from bones and purifying bone black in medicine and as a laboratory reagent.
Okay, so these are the common uses of hydrogen chloride. It will be used in the manufacture of chlorine, then ammonium chloride, then glucose, then for extracting glue from bonds. Okay, in certain industrial purposes also we are using this hydrogen chloride. Then purification of bone black, then in medicine and as a laboratory reagent. So you have to go through these uses and you should identify which use belongs to which compound. We are familiar with different compounds and their uses in this chapter itself. Okay, so do not get confused with these uses and the compounds and elements. In the case of certain common uses, that's common for everyone, but there will be a specific uses for each compound. Okay, so you should familiar with that specific use of each compound or element. The P block. Clear, children? Then the next one about oxo acids of halogens. Here, in the case of oxo acids of halogens, only need to learn the structure. So these are the structures of oxo acids. Which are they? First one is hypochlorous acid. Okay, hypochlorous acid. Its chemical formula is HOCl. HOCl. Here you can see oxygen atom at the center, then hydrogen and chlorine at both sides. So you should familiar with this structure. So first one, that is hypochlorous acid. Then the next one is chlorous acid. Okay, chlorous acid, HOClO. Okay, HOClO. The next one is chloric acid. Can see one chlorine, 3 oxygen atoms and 1 hydrogen. The next one is perchloric acid. Perchloric acid. So these are the oxo acids of halogen. Which are they? Hypochlorous acid, then chlorous acid, chloric acid, perchloric acid. So you must familiar with the structure of all these oxo acids of halogen. Okay. There is only small difference between the structures. When you look at the first and second, hypochlorous and chlorous. In the case of chlorous, one more oxygen atom, right? It is attached to chlorine with double bond. If you are drawing one more oxygen atom with double bond, it will be chlorous acid. Okay. With hypochlorous acid, you are drawing one more double bond with oxygen atom. It will be chlorous acid. Okay. The next one in the case of chloric acid and perchloric acid, one more oxygen atom is drawn here with chlorine. It will become perchloric acid. So there is small difference in the structure between chloric and perchloric, then hypochlorous and chlorous. And in the options itself, there will be a small difference. Okay, so you should learn the structure very well. Otherwise, there will be confusion in the options. Okay. Okay, then we are moving to the last part of this group 17, that is interhalogen compounds. Okay, interhalogen compounds. What's the meaning of interhalogen? The compounds formed between these halogens itself. Fluorine, chlorine, bromine, iodine, etc. So the compounds formed between these elements, it is known as interhalogen compounds. When one halogen combines with other halogen atom, then the compound formed is known as interhalogen compounds. Okay. And interhalogen compounds can have the following formulas. XX dash. Okay. XX dash. Then XX dash 3, XX dash 5, and XX dash 7. X stands for one halogen, then X dash stands for another halogen. Okay. So here X, capital X is the larger halogen atom than X dash. Okay. So we can write the formula of interhalogen compounds XX dash. Then XX dash 3, XX dash 5, XX dash 7. So there are two atoms, right? X and X dash. So always X is larger halogen atom than X dash. Clear, children? X is larger halogen atom than X dash. And X is more electropositive than X dash. X is more electropositive than X dash. Clear? Is this clear? Then as the ratio between radii of X and X dash increases, the number of atoms per molecule also increases. The ratio between the radii of X and X dash increases, the number of atoms per molecule also increases. So there will be more atoms present in F and I, because the large difference between the halogen that occurs in the case of fluorine and iodine, because fluorine at the top of the this halogens and iodine at the bottom, right? So there will be large number of groups formed by this fluorine and iodine, because the ratio between radii of X and X dash increases, the number of atoms per molecule also increases. So here the large difference between the radii that occurs between fluorine and iodine. That's why. And its formula is IF7. IF7. Okay. And can you identify which one is the X and which one is the X dash? From this IF7, which one is X and which one is X dash? Anyone?
Ma'am, from which one?
IF7. In IF7, that's the formula of the molecule, right? Can you identify which one is X and which one is X dash? Here I told you X is the larger halogen atom than X dash, and X is more electropositive than X dash. So when we are comparing this iodine and fluorine, which one is X and which one is X dash?
X is I.
X is X.
X is Tell me. Which one, iodine or fluorine? Yes?
Iodine.
Yeah, iodine. Then X dash is fluorine. Because when we are comparing iodine and fluorine, iodine has larger size compared to fluorine. Then the electropositive nature also more for iodine because fluorine is the highest electronegative element, right? So X is iodine, then X dash is fluorine. And very simple method when we are looking this general formula, X only one element, X dash 7. So here it is IF7. So fluorine is X dash, iodine is X. Okay. Clear, children? So they have certain general formulas, X dash, X dash 3, X dash 5, X dash 7. And X is the larger halogen atom than X dash. X is more electropositive than X dash. As the ratio between radii of X and X dash increases, the number of atoms per molecule also increases. And the maximum that's shown by this iodine and fluorine, and their formula is IF7. Clear? So it's clear, children?
Yes, ma'am.
Okay, then we are moving to the preparation of this interhalogen compounds. Preparation. So interhalogen compounds are prepared by direct combination of two halogens. Okay, then the product formed depends upon the conditions given. So here just the combination of two halogens to form interhalogen compounds. You can see here, first example, Cl2 plus F2. Chlorine and fluorine join together. But here the condition is equal volume is needed and the temperature should be maintained 437 Kelvin. Okay, equal volume of chlorine and fluorine atoms, then 437 Kelvin. Then 2 ClF is formed. That's in the general formula XX dash. Okay, XX dash. Clear, children? If equal volume of chlorine and fluorine combined together at 437 Kelvin, then ClF is formed. Chlorofluoride. Okay, ClF. The next example, the same atoms, chlorine and fluorine, but here this fluorine in excess. In the first case, equal volumes of chlorine and fluorine is taken at 437 Kelvin, then ClF is formed. Here excess amount of fluorine along with chlorine. They combine together at 573 Kelvin, then ClF3 is formed. That's in the formula X3. Okay, X3. So in the first case, equal volume 437 Kelvin. Second case, excess of fluorine at 573 Kelvin. And the third one, that's about the combination of iodine and chlorine. Equimolar, that means equal amount of their molarity. In the case of iodine and chlorine, when they combine together, ICl is formed. Here also in the formula XX dash. Okay, XX dash. Then the same iodine and chlorine, but the chlorine is in excess. Then ICl3 is formed. Here the formula is XX-3. XX-3. Then the next combination with bromine and fluorine. Okay, bromine and fluorine. And here the condition is it is diluted with water. This diluted with water. Then BRF3 is formed. That's also in the formula XX-3. Okay, then the last one, that's the bromine and fluorine. Here fluorine is in excess and BRF5 is formed. BRF5. Their general formula XX-5. So these are the preparation methods of interhalogen compounds. Here just the combination of halogen atom, but specific conditions are required for this reaction to take place. Okay, the first one you know that equal volume of chlorine and fluorine at 437 Kelvin, then ClF is formed. Then the second case, excess of fluorine is needed and the temperature should be 573 Kelvin, then ClF3 is formed. Then iodine and chlorine in equal amount, then ICl is formed. Okay, then the next one, iodine and chlorine. Chlorine is in excess, so ICl3 is formed. Then next one, bromine and fluorine. Here diluted with water, BrF3 is formed. Last one, bromine and fluorine, and this fluorine is in excess, BrF5 is formed. So these are the different preparation methods of interhalogen compounds. It's just a direct combination of two halogen atoms, but specific conditions are required for the reaction to take place. Okay. So that's about their preparation. Then we are moving to the properties of this interhalogen compounds. Properties of interhalogen compounds. So these are all covalent molecules. Okay, sharing of electrons between these atoms take place, and they are diamagnetic. Diamagnetic means paired electrons are there in magnetism. Okay, paired electrons are there. That's why it is diamagnetic. Then they are volatile solids or liquids. Okay, volatile solids or liquid. Volatile means they can be converted easily into the form of vapors. Volatile solids or liquids at 298 Kelvin. 298 Kelvin. And there is one exception, that's in the case of CLF. Okay, CLF, which is a gas. All other compounds are volatile solids or liquids at 298 Kelvin except CLF. It's in the form of gas. So you have to note that. Okay, it's an exception. It's important. It's in the form of gas. All other volatile compounds, they are available in the form of solids or liquids at 298 Kelvin. And their physical properties, that's intermediate between, their physical properties are intermediate between those of constituent halogens, except their melting point and boiling point are little higher than expected. Okay. Their physical properties are intermediate between those of constituent halogens, except their melting point and boiling point are little higher than expected. All other physical properties are intermediate between the constituents of halogens. Which are the constituents of halogen present in that compound? Physical properties are intermediate between those. Okay, but in the case of melting point and boiling point, it is little higher than expected. Clear, children? So the remaining physical properties includes their atomic radii, ionic radii, electronegativity, then ionization enthalpy, electron gain enthalpy. Everything is similar to that of halogens, intermediate between those of halogens. Then here the boiling point and melting point, it's higher than expected. That's it. Clear? Is clear? Yes. Then the next point, interhalogen compounds are more reactive than halogen except fluorine. Okay, interhalogen compounds are more reactive than halogen except fluorine because XX dash bond in interhalogens is weaker than XX bond in halogen except FF dash bond. Okay, here fluorine is an exception, but the case of other interhalogen compounds, they are more reactive than this halogens except fluorine because XX dash bond in interhalogens is weaker than XX bond in halogens. So this XX dash bond, it will be weaker than XX bond. XX bond means same halogen combined together to form a molecule. Okay, XX dash means different halogens combined together to form a molecule. So in the case of XX dash, bond in interhalogen is weaker than XX bond. That means it is easy to break the bond between these atoms, so it will be more reactive. Clear? That's why these interhalogen compounds are more reactive. Clear, children? The bond between these two, it's weaker. Okay, so it's very easy to break this bond and they can involve in chemical reactions. Here the exception is in the case of fluorine. In the case of fluorine, this F dash bond, it's very much stronger. Okay, clear? Fluorine is an exception. Then the case of remaining interhalogen compounds, they are more reactive. The reason is that bond between XX dash, that's weaker. So it's easy to break the bond and involved in chemical reactions. And all of them undergo hydrolysis. What is hydrolysis? Hydrolysis. Tell me, children, what is hydrolysis? Emmanuel, what is hydrolysis?
Adding with water.
Yeah, addition of water, right? So all this interhalogen compounds, they undergo hydrolysis. When they react with water molecule, HX dash and HOX is formed. Okay, XX dash react with H2O. XX dash means interhalogen compound. This interhalogen compound react with water molecule. HX dash plus HOX is formed. And here in the next point, you can see the structures of these molecules, this interhalogen compounds. XX3, it has a bent T shape. XX3, it has bent T shape. Here there is one table in table 7.11. Here you can see that the shapes. Okay, XX3, that's bent T shape. Then XX5, there are different, square pyramidal shape. There is a common structure for this general formula. XX3 bent T shape, XX5 square pyramidal, then IX7. It has a pentagonal bipyramidal. IX7. You can also write this XX7. XX7. Okay. XX7. That is pentagonal bipyramidal. That's about the structures of this interhalogen compounds. XX3 bent T shape, XX5 square pyramidal, XX7 pentagonal bipyramidal. So you can just mark the structures. Okay, children, table 7.11. And it is based on VSEPR theory. Do you remember VSEPR theory that you have learned in +1, valence shell electron repulsion theory? So based on this VSEPR theory, the structures are assigned to each interhalogen compound. XX3, it has a bent T shape. XX5 square pyramidal, then XX7 pentagonal bipyramidal. So any compound that comes in the general formula, XX3, XX5, XX7, you have to follow this shape. Okay, for the first one, you can write the example. Br, then Cl3. Okay, for BrCl3, it will be bent T shape. Then when we write BrCl5, it will be square pyramidal. Then the case of IF7, it will be pentagonal bipyramidal. So you have to learn this general formula. And if any molecule that suits to this general formula, it has a common structure, bent T shape, square pyramidal, pentagonal bipyramidal. Clear? It's clear, children?
Yes.
Okay.
Yes,
Then the next one about uses. Okay, uses of this interhalogen compounds. Dia, can you please read the uses? Page number 207.
These compounds can be used as non-aqueous solvents. Interhalogen compounds are very useful fluorinating agents.
Yeah.
ClF3 and BrF3 are used for the production of UF6 in the enrichment of U235.
Yeah, uranium. So these compounds are used as non-aqueous solvents. Non-aqueous solvent means without the presence of water. Okay, this can be used as solvent and water is not there. Okay, that's the first use. Then interhalogen compounds are very useful fluorinating agents. What's the meaning of fluorinating agent? Children, switch on your videos. Fluorinating agents mean they can able to donate fluorine atoms. Okay, that is fluorinating agents, adding fluorine to the chemical reaction. Then the ClF3 and BrF3, it is used for the production of UF6. Okay, that's a compound formed with the combination of uranium and fluorine. Okay, uranium and fluorine, that is UF6. in the enrichment of uranium-235. What's the use of uranium? Uranium. It's used as a fuel in nuclear energy, right? Or nuclear reaction. So for the enrichment of uranium, we can make this reaction. Uranium combined with the ClF3 or BrF3, UF6 is formed. Okay. So these are the uses of this interhalogen compounds. Clear, children? Any doubt about interhalogen compounds? Clear, right? Okay, so we have completed group 17. Then the next part is about group 18. So group 18, what's the common name? Group 18?
Noble gases.
Yeah, noble gases, or otherwise known as noble gases or Rijas.
Inert.
Yeah, inert gases. They are known as noble gases or inert gases. They do not take part in chemical reaction because they have a stable, completely filled configuration. They are very much stable compared to other elements in the periodic table. So they do not take part in chemical reaction. But in this portion, we will learn about certain exception, certain noble gases or inert gases. They will react with other elements to form compounds. Okay. That we will learn in this section, the chemical properties. Xenon fluorine compounds and xenon oxygen compounds will be there. Okay. So which are the elements present in this category? Noble gases, group 18, or inert gases? Emmanuel, can you tell me the name?
Helium, neon,
Helium.
argon,
Hmm.
crypto,
Hmm.
xenon,
Hmm.
radon,
Hmm.
organazole.
Organazole. Okay. So these are the elements present in group 18. Among this helium, neon, argon, krypton, xenon, that's considered as noble gases. Radon, it's a radioactive element. And this organazole, it's also a synthetically radioactive element. Okay. Then in the case of helium, there is an exception in their configuration. It has a 1s2. Okay, completely filled S configuration. But in the case of all other elements in this section, they have completely filled eight electron in their outermost shell. In the case of helium, only 2 electrons in their outermost shell. Then we can discuss each topic in the next class. Okay, children? Okay, then let me take your attendance. Just wait. Okay, then thank you, children. See you in the next class. Bye.